Go ahead, Tim.
Hi, Tim. It's a pleasure to welcome you this evening as our guest speaker. It's going to be a fascinating talk. You did see the very truncated bio that Tim sent with his synopsis of the talk, but as always, he's very modest. He did mention a few things, but I just want to add that Tim is probably one of the most experienced, the most authoritative, and the most respected members of ASSA. If you look at the Sky Guide, at the page which verbalizes awards and officials, you'll see the name Timothycooper cropping up all over. He's a past president of ASSA. He's an honorary member of ASSA. He's got a long service award from ASSA. I think he's got 2 President's Awards. And then in 2018, he did refer to that in his bio. He got the Overbeek Medal, which is the highest award that ASSA can give for observational work. And it did make a brief mention of tracking meteorites down to Botswana. When he got the Overbeek Medal, he gave a talk on that, which was absolutely fascinating. And I think I must still twist Tim's arm to give the Mars Astronomy Centre a repeat of that fascinating detective story. Tim, there's no one more authoritative to talk about meteors in South Africa, and we're looking forward to whatever of your semi-infinite knowledge you're going to share with us tonight. Over to you.
Thank you, Pierre. Derek, are you seeing my screen?
Yes, we are. You can go ahead. Thanks, Tim. I'm going to mute my mic and video for now.
Thank you. And thank you, Pierre, for the introduction. And it's a great pleasure to talk to you tonight about monitoring meteors with video cameras. I'll give you an update on the Global Meteor Network of South Africa, or in South Africa. Did that screen change? Did the slide change?
Yes.
Okay.
Yes,
super. So
muted.
Thanks. Just as an agenda then, we're just going to recap what meteors are. Then I want to give you a little bit of history about the triangulation of meteor orbits over the last 300 years. I know that there are some educators online tonight, and so I've put a little bit of history in there as well as the science. We'll talk about the rise of video recording surveys, and then we'll move on to the Global Meteor Network, talk about what it is and how you can participate, and then wrap everything up in terms of some conclusions. So meteors are the debris left behind by comets and asteroids as they pass around the sun. This is an example of a cometary nucleus. It's Comet Churyumov-Gerasimenko. It's an image that was taken by the Rosetta probe, which went into orbit around the comet in 2015. And what you see there is a solid body. And while it's way away from the sun, outside of the warming influence of sunlight, it's a solid body comprising frozen gases and ices, predominantly water vapor, carbon monoxide, carbon dioxide, and within that matrix then are entrapped dust particles. So as the comet gets closer and closer to the sun, it comes under the warming influence of sunlight. Those 3 predominant volatiles, water vapor, carbon monoxide, and carbon dioxide, they start to sublimate, and they release dust grains into the orbit of the comet, which can continue on an orbit very similar to the comet itself. And so you can see here that that process has started. The nucleus is what we call switched on, and it's starting to emit dust grains into its environment. So the Rosetta probe captured this image, and also at the same time it collected samples of the dust from that comet, and this is an example of the dust particles that it captured in the spectrograph. These dust particles were analyzed There are around about 55% of inorganic materials, which are mainly silicates, calcium, magnesium, and iron silicates, with smaller amounts of aluminium and sodium. So these are the particles given off by the comets, and if these particles come into our atmosphere and burn up, traveling at high speed, those are what we see as meteors. To give you some idea of the size of those particles, there are 4 screw heads on there, and those screw heads have a diameter of 1.5 millimeters. So the dust particles given off by this cometary nucleus are very small, and those are the typical size of meteors that you would see if you go out on any one night and look up and you see a meteor. That's the type of particle that results in that. At the same time, we know also that particles are given off by asteroids as they go around the sun. The most well-known is an asteroid by the name of 3200 Phaeton. It's the parent body of the Geminid meteor stream. It's a meteor stream which is visible every year, reaches its maximum on the 13th or 14th of December, and we'll be able to see that meteor shower later then this year. And so those particles are particles which are given off by an asteroid. And this is another asteroid. It's an asteroid called Bennu. It was visited by a space probe called OSIRIS-REx, which when it arrived at the asteroid in 2018, it actually saw these particles that you can see on the left-hand side here being emitted from the surface of the asteroid. So once again, if these particles come into our atmosphere, they will be seen as meteors. So that is OSIRIS-REx arriving at Bennu. OSIRIS-REx also deposited a probe down to the surface. It collected a sample. This little probe that you have here actually impacted onto the surface of the asteroid and collected a small sample. And that canister that you see there was actually returned to Earth. And at the bottom here, you can see the canister, and it was opened in January 2024 to reveal this material here. So this is actual material which has been taken, the sample from the surface of an asteroid and brought back to Earth. The average particle size that you see there is around about 1.5 millimeters. So about the same size as the screw heads that you saw on the slide from the cometary dust. Once again, mainly silicates, calcium, magnesium, and iron. Iron also in the form of magnetite. Right, so these are the typically what the particles that we see as meteors when they come into the Earth. We know exactly what these particles are nowadays. So it's useful then to just consider the definitions that we have in terms of meteors. And these definitions were agreed on at the IAU meeting on the 30th of April 2017. So a meteoroid is a solid natural object of a size roughly between 30 microns and 1 meter, moving in or coming from interplanetary space. So those particles, before they come into our atmosphere, they are termed meteoroids. A meteor is the light and associated physical phenomena which result from the high-speed entry of a solid object from space into a gaseous atmosphere. So once those particles come into our atmosphere and they burn up, that is what we then see as a meteor. And those particles are very small. We don't see the actual particle burning up. What we see is the effect it has on the atmospheric gases because these particles are traveling at very high speeds. So that's a meteor. A meteorite is any natural solid object which survives its passage through the atmosphere, and it then basically reaches the ground. So when you look up and you see a shooting star, it's not a meteorite, it's a meteor. It only becomes a meteorite if it hits the ground and it is recovered. A meteoroid stream is a group of meteoroids which have similar orbits and a common origin. In other words, they are a stream of particles which come from the same comet or asteroid. And then by the same token, a meteor shower is a group of meteors, in other words, coming into our atmosphere, which have been produced by the same meteoroid stream from a parent comet or from a parent asteroid. And then we term any meteor which is brighter than the apparent brightness of Venus, so around about visual magnitude -4, that's what we call a bolide or a fireball. And then any meteor brighter than absolute visual magnitude -17 is then called a super bolide. Right, so I think let's just come back to this term meteor shower. So a meteor shower is a group of meteors produced by meteoroids of the same meteoroid stream. In other words, they've come from the same comet or asteroid. Okay, so that's very important. So this is a computer simulation of the Geminids I mentioned earlier that came from asteroid 3200 Phaeton. So this is the computer simulation of the actual meteoroid stream. Here you've got the orbits of Mercury, Venus, and the Earth. And if the Earth passes into that stream, we then get a meteor shower. So this is the debris which has been left behind by asteroid Phaeton. Now, we know this is the case, and because we know it's Phaeton, we know where Phaeton is in its orbit. So somewhere in that stream is the asteroid Phaeton. And if it crosses the point where the meteor stream crosses Earth, then it's possible that we could have an impact of that asteroid with the Earth. Because we know it's Phaeton and we know that exactly where it is in its orbit, we know that Phaeton is not likely to cause an impact with the Earth in the next 400 years. But what in the case that there is a meteor shower that we don't know what the parent body is? It means that somewhere in that stream is a body which in the future could impact the Earth if the Earth and the parent comet or asteroid are in the same place in time. Right, so a little bit of history. Going back to Edmund Halley, at the time that he was doing his pioneering work on cometary orbits, the actual nature of meteors wasn't known. It was surmised that meteors were actually the terrestrial phenomena, basically things like sulfurous vapors which were igniting in the atmosphere. And then on the evening of the 19th of March, 1719, there was a very, very bright bolide. It was a super bolide, and it was widely seen over most of England and Scotland, and also over parts of northern France. Edmund Halley, being the good astronomer that he was, he managed to collect reports of the object. And in particular, he collected reports from 5 eminent scientists in the UK. He managed to triangulate the path from the observations that they made, and he came out with a path for the object, and he determined that the altitude of the meteor was around about 65 miles above the village of Pristane. That's actually a very good agreement, because 65 miles is 105 kilometers, and nowadays we know that is about the altitude at which meteors burn up in our atmosphere. So he came to the conclusion there then they abundantly evince the height thereof to have exceeded 60 English miles, which is right at the top of the atmosphere. So that was Edmund Halley in 1719. In 1794, Ernst Chladni in Germany, he produced a catalogue of recorded observations of fireballs. And then in 1798, he showed that meteors could not be explained from the accumulations in the upper regions of our atmosphere. For that work, Ernst Chladni is nowadays known as the father of meteoritics. For the historians who might be in the audience today, Ernst Chladni had another claim to fame. He's also known as the father of acoustics for the work that he did on sound generated by metal plates. In the same year, 1798, 2 Germans also conducted visual observations of meteors. Brandes and Benzenberg, and they managed to show that the meteors must come from outside of our atmosphere. The first relation of meteors as debris from comets came with the appearance of the meteor storms, the Leonid meteor storms. There were very, very prolific storms from the Leonids in 1799, in 1833 and 1866. And astronomers realized that these storms coincided with the return of comet 55P Tempel to its perihelion in its 33-year orbit. So on the right-hand side, you can see there a woodcut. It's a famous woodcut by a person called Adolf Folmy. He produced a woodcut in 1833 on what's known as, this was a meteor storm. A meteor storm is any meteor shower where the rate is more than 1,000 meteors per hour. And on this particular occasion in 1833, it's estimated that meteors fell at between 50,000 and 150,000 meteors per hour. Further associations then took place, first of all, with the Perseids in 1866. They showed a meteor storm, which coincided with the return of comet Swift-Tuttle in its orbit. And then again with the April Lyrids in 1867, with the return of comet 1861 Thatcher. So at this point then, astronomers knew that these meteors were derived from parent comets. The first person to photograph a meteor was Ladislaus Weineck. After the breakup of Biela's comet in 1846, it was shown to have two fragments. Astronomers looked for the comet again in 1872, but couldn't find it. And in its place, there was a very prolific meteor shower, which we now call the Andromedids. So Weineck decided to try to double station photograph these. And he set up two stations, one in Prague and one in Jena in Germany. Unfortunately, he didn't manage to capture a double station image of a meteor, but he did manage to image a meteor, one single meteor on the night of 27th of November, 1885. So in preparing this talk, I realized that 27th November, 1885, in just over a week's time, it'll be the 140th anniversary of the first image of a meteor. For some reason, my thing has frozen. Oops. There we go. Got it back. His work was followed up then by Louis Elkin. Louis Elkin is a name known to South African astronomers. He was invited to the Royal Observatory at the Cape by Sir David Gill, and there together they did work on stellar parallaxes. And then when Louis Elkin went back to the United States, he set up meteor cameras to monitor meteors. He had a rotating shutter and in front of the camera, and because he knew the rotation rate of the shutter, he could actually work out the speed of the meteors. So he did some pioneering work on the first images with a rotating shutter in 1889. He continued that work up until around about 1910, when Fisher and Olmsted at Harvard College Observatory started to produce catalogs of meteors. And that work was then continued by Dorrit Hoffleit in 1930, including images which were taken at the Boyden Station near Bloemfontein, of which this is an example here. This is an image of a meteor taken with a rotating shutter, and it's actually cut the meteor up into sections so that you can actually then work out the speed of the meteor. The first video observations of meteors came with the Alpha Monoceratids. This is a meteor shower which had outbursts in 1925 1935 and 1985. It was predicted again to have another outburst in 1995 due to perturbations of the shower by the planets Jupiter and Saturn. And so the several members of the Dutch Meteor Society set up video cameras, and they succeeded in capturing double station images of 7 alpha monoceratids, which enabled them to determine the orbit of the object. We now know that the alpha monoceratids is basically formed by a comet which has a period of more than 140 years. So at that some stage, this comet will come back again. And if it comes back at the same time that the Earth is in a similar position, there's also a possibility that comet could be a potentially hazardous comet. So this was the alpha monoceratids. And just by the way, the alpha monoceratids had another outburst in 2019, which was also well captured on video. So that was the 5th recorded outburst of this meteor shower. The whole outburst of the meteor shower took place within less than half an hour. The meteor rate went up to around about 500 per hour, but the whole show was over within half an hour. So based on the success of that first video detection of meteors, there started to become interest in global monitoring of meteors using video. The first video survey was the Timothycooper survey in Japan that started in 2003. But the first really global efforts to monitor meteors came with the cameras for All-sky Meteor Surveillance, or called CAMS, that saw first light in 2010. Today, there are more than 500 cameras worldwide, and it's captured already 3.58 million meteor orbits up until last year. In the Southern Hemisphere, we've got several stations now. In Southern Africa, we've got cameras in Namibia, and we've got 16 cameras in South Africa, which I operate, some of them in my backyard, and the other ones at the Hartebees Hoek Radio Astronomy Observatory. And these are my cameras on the right-hand side. So these are the CAMS cameras. It's a Watec 902. I've got a bank of 8 cameras, and that's the little enclosure that I've got just in the process of being set up and before it was commissioned. So CAM's objective is an automotive video surveillance of the night sky to validate minor showers in the IAU working list of meteor showers. Just after the start of CAMS, then there's another group here in Croatia. This was the Croatian Meteor Network. And the Croatian Meteor Network then decided to expand their network globally. And that was the nucleus that formed the Global Meteor Network. So the Global Meteor Network, which started off in Croatia, it was established in 2018. It today has more than 1,000 cameras worldwide. So far, it's detected around 2.6 million meteor orbits, and it's growing very, very rapidly. This is the most rapid growing meteor survey that there is now, due to the low cost of the cameras. You can see on the bottom here the map of where the cameras are worldwide. There are a lot in the UK. In fact, the United Kingdom is almost completely covered now with cameras. New Zealand in the Southern Hemisphere, there are cameras all over the island there. And so they fit with the slogan, the GMN objective, to have no meteor unobserved. Now, you can see in Southern Africa here, there's a little tip there at the bottom of the Western Cape. There are a few cameras in operation there. But in general, on the African continent, we really need to start to build a network so that we can meet the slogan of no meteor unobserved. And bear in mind that where we are in terms of the globe, we're at a unique latitude and longitude, so that if a meteor shower occurs in the Southern Hemisphere at this latitude here, it wouldn't be visible from South America or Australia. We're the only ones that would be able to see it. Hence the importance of growing our network in Southern Africa. So in terms of the growth of the Global Meteor Network cameras, starting off in 2019, going up to the current state, we have 1,162 cameras around the globe. You can see the progression in the amount of meteors which are captured per year. Sometime during 2026, we'll exceed 1 million meteor orbits captured. So it's a very rapid growing meteor network. In terms of Southern Africa, currently this is the current state. I mentioned in terms of cams, we have 62 cameras in Southern Africa. We've got 48 of them are in Namibia, including at the HES Observatory. And then we've got my 16 cameras, 8 of them in my backyard, and 8 of them at the Hartebeespoort Radio Astronomy Observatory. In terms of the Global Meteor Network, we currently have 13 cameras. Most of them are in the Western Cape. There are 2 here in Gauteng, which are operated by Paul Ludik. And Paul desperately needs some more cameras around him to interface with his cameras, because if you don't have cameras facing each other, you can't do double station work. You can monitor meteors, but you can't determine their orbits. So that's what we have in the moment in the Western Cape. We've got 11 cameras in the Western Cape, and we're busy looking at growing this network. And of course, we want to grow in and fill gaps within the country so that we've got a network pretty much across the whole country. So you can participate in this. You only need 1 camera to start, provided you have it orientated in the right direction so that you can overlap with other cameras in the network. What is the network? What is the Global Meteor Network? So it's a global decentralized network of over 1,000 amateur and professional astronomers using low-cost video cameras to monitor and analyze meteors. Its primary goals then are to observe and characterize meteor showers and outbursts, increase the number of instrumentally observed meteorite falls, and to use collected data to better understand the solar system's meteoroid environment. It works with a very simple setup. You have a camera which you can mount on the wall outside. You can mount it on the roof. You can mount it on the side of a chimney as well if you want to, so long as the chimney is not in operation. So you have your camera. It looks nothing different than a normal security camera. It's connected to a Raspberry Pi computer, and then you need a Wi-Fi router so that you can upload and download the information, which it does pretty much on a daily basis. Typical parts here. Here's the housing. Here's the camera, which goes inside, and here's all the other attendant parts. All of these parts are available on the GMN's wiki page. There's a complete list of what you need, everything that you need to buy, where you can buy it, and how to assemble it. You can either build your own camera, or you can also buy a ready-made camera and just put it up. I'm one of the latter. I prefer the plug-and-play option. So rather than building cameras myself, I'd rather buy the camera and just get going. So that's the simple setup. This is the 2 cameras that we mounted. We have 4 cameras at 2 schools in the Western Cape as part of our outreach program. These are the 2 cameras at Toast-Revere Primary School. They've been operating now for around about 18 months, just watching the night sky every night, picking up meteors and processing them. So once you've got your camera mounted, then you need to point it in the right direction. And we have a pointing tool to do that. So we use the pointing tool. You just input your camera details, the nature of the lens that you use, the your location on the Earth. And based on that, we work out the right overlap so that you overlap with other cameras in the network, and that maximizes the number of meteors that we see coming into the atmosphere at an altitude of around about 100 kilometers above the Earth's surface. Okay, so that's the pointing tool. And so once you've done that and you're set up, this is typically what will happen. So this on the left-hand side is a meteor which has been captured with a camera from one station. In this case, I think this was from Langsberg High School. There is a meteor captured from Toastrefear. So if we just oscillate between these, it's the same meteor. It's been captured with the same type of camera, but from the two different sites. So if you then basically, and the software will do this for you, if you triangulate those, we can then find the path of where this passed across the Earth's surface, and we can also work out the orbit and the radiant from the particular meteor shower that it emanated. Your camera will also, you'll be able to go online and actually see what all the cameras are looking at each night. So there is what we call the camera status page. This is a typical example. So this shows the locations of all the cameras that we've got in the Western Cape, one in the Eastern Cape as well. You can just click on the thumbnail that you see here, and it will then bring that camera up. So if we were to click on camera ZA0008, for example, this camera is at Langsberg High School. Clicking on that brings up the dashboard. On the dashboard, you can see basically all the results for the latest night. Or you can click on the archive button, and the archive will bring up all the data for any night that the camera has been in operation. So you can scroll through those and see exactly what the cameras are seeing. In this particular case, if you look at the latest night here for 8th of November, you can see that on the right-hand side here is all the captures, everything that was captured by the camera. It includes meteors, it includes satellite trails, it includes aircraft, it includes insects and bats. Anything which the camera picked up is on that particular stack there. The software filters everything out that it doesn't want, and it then gives you the meteors which are left over. Those are the meteors which will then be processed. At the bottom here, you can see that there are a number of thumbnails for all the meteors that were captured. And then if you scroll further down on the dashboard, you come to a video where the whole night's captures are compressed into a video which is 1 minute and 25 seconds long. And so if you look here, you can see that on the total detected stack, there's an object here. On the meteors detected stack, it's there. And you can see the same at the bottom here. Third from right is that meteor again in the thumbnails. If you go to the video, you can extract the image of that, and there is the image of that particular meteor streaking across the sky with quite a long path and ending up behind the clouds. It's great fun to do that, and also for schools, it's great fun to look at these videos, because you can also, during the process, see if you can work out as they go across the sky, the constellations. It's a great way to learn the sky without actually going outside. You can do everything from sitting in front of a screen. The other thing the software will do is it will then basically calculate the trajectory of the meteor, and it will backtrack it to the particular radiants that were active. So for this particular night, Langsberg High School picked up all of these meteors coming from these showers: the Southern Taurids, the Chi Taurids, the Omicron Eridanids, the Andromedids, and the Northern Taurids. So these showers here were all picked up. Meteors were picked up from these meteor showers active. And then there were, in addition, 30 meteors which were not backtracked to any particular radiant. We call these sporadic meteors. So in this case, there are 5 meteors from 5 different meteor showers picked up from Langsberg High School on that night. They get fed back into the global database. So once you add those to the global database, this for the same night is all the meteors which were collected from all of the cameras around the globe, including from Langsberg and including from all of the other cameras in South Africa. So that's for one night. These are all the radiants for 1 week. In other words, the week from the 1st to the 8th of November. And then these are all the active radiants for the previous month. So in this case, the month of October from the 1st to the 31st. These were all the meteors, meteor radiants which were active, everything identified here by a white ellipse. And there are no less than 66 meteor showers. Well, I counted 66, there might be a bit more, but I counted 66 meteor showers active during October of this year. Included in those 66 is a meteor shower at the bottom here. It's labeled as M2025S2, M2025S2, and that is a brand new meteor shower which was discovered in October of this year, or September, October this year. And the South African cameras participated in the discovery of this new meteor shower. It was announced on electronic telegram number 5613. So a new meteor shower on the Jupiter family comet orbit was detected during 2025 September 9th to October 1 by the Global Meteor Network. 377 meteors, and South African cameras participated in this new discovery. And there you can see an enlargement of the discovery from the GMN cameras, and you can also see that the same shower was picked up by our CAMS cameras as well. So it's great to see these new showers being discovered all the time. In this case, again, we don't know what the parent comet is. We know because we've triangulated these 377 meteors, we know exactly what their orbit is, but at this stage we don't know what the parent comet is. That remains to be discovered. So how many showers are there? In terms of the annual meteor showers, these are the very well-known showers like the Geminids, which I've mentioned, the Leonids, the Orionids, the Taurids, etc. These are showers which are fairly prolific. They come back each year, and there are around about a dozen meteor showers, annual meteor showers. The International Astronomical Union working list has a list of 830 meteor showers, and all of the known showers which have been detected by video cameras, either GMN or by CAMS, have now been listed in the Atlas of Earth's Meteor Showers, which was written by meteor astronomer Peter Jenniskens. He published this Atlas of Meteor Showers last year, and in that atlas there are 513 confirmed meteor showers. Out of all of those meteor showers, there are only 36 that we know the parent body. And that means that there are literally hundreds of meteor showers that we know of which intersect with the Earth's orbit that we don't know what the parent body is. So these meteor showers then are the smoking gun for a potentially hazardous comet or asteroid that if it comes back in the future, it could be potentially on an impact with the Earth. Okay, so just an example of what's in the Atlas of Earth's meteor showers. This is just cut from a page. This is an example for the meteor shower called the Volantids. Their shower code is 758 VOL. You can see all the details here about what we know about them. You can see the type. You can see the years in which it's had outbursts, the period that it's active, in other words, from December 27 to January the 1st, and then the orbital details. Brief history, New Year's Eve shower on the southern hemisphere. It gets that name because it was first detected on the evening of December the 31st, 2015 by the CAMS cameras in New Zealand. It's a bit unfortunate because since this shower was discovered on New Year's Eve in 2015, nowadays I don't get to celebrate New Year like everybody else and going out to a party. New Year's Eve, you'll find me, if it's clear, outside under the sky looking for fireworks of the celestial kind. Just on the left-hand side then, you can see these are all the meteor streams which are active between the dates of 1st and 10th of January. And you can see right at the bottom there, 758 Volantids, there is the stream. in these meteor maps. It's also very important to monitor fireballs using these cameras. It's one of the objectives of the Global Meteor Network. I mentioned to you before that the definition of a fireball is any meteor which is brighter than Venus or around about -4 or brighter. And some of these fireballs, if they are large enough, they could potentially survive their passage to reach the ground, the Earth's surface. And if so, then we can find them as a meteorite. The great importance, if you can capture a fireball on 2 cameras, we can actually triangulate, we can determine its orbit, we can determine its path, and also determine the location where it may have fallen if it is to be found as a meteorite. So there's a selection of bright fireballs here taken with different cameras, and you can see the date. On the bottom here, you can see that these bottom 4 here, they're all on the same date. It is in fact the same fireball which was captured on no less than 4 different cameras within the Western Cape network. So that's the importance of monitoring fireballs in the hope that we can find meteorites. We unfortunately missed a trick very recently. On the 3rd of August 2025, there was an extremely bright bolide, a super bolide, which passed across southern Botswana. Unfortunately, we did not capture it on any GMN cameras because we don't have any in this region. All we've got to go on is a number of security cameras, and we've collected footage of this fireball from no less than 42 different security cameras. The unfortunate thing is that we then have to go to each one of these cameras and calibrate them so that we can actually measure the trajectory from this. And that's quite a tedious progress. And had we had the GMN cameras in place, we would have been able to triangulate this bolide and then probably find the full location very quickly of any potential meteorites. Okay, so how can you participate? There are a few ways that you can do this. First of all, you can join the project and install a GMN camera. You only need to install 1 camera to get started. You can, of course, install as many as you want, but one camera is enough to get started. There's a wiki page which has all the details on buying a camera or building your own. The web address is there. So that's if you want to do that as an individual. And several people in South Africa have already started to do that. For schools and educators, we have the GMN outreach program where we have a number of cameras which have been sponsored by an anonymous benefactor. And we've already put 4 cameras in the Western Cape, 2 at Toastfield Primary School and 2 at Langsburg High School. Those cameras have been operating now for around about 18 months and doing quite well. We want to expand that program, and we're looking for new schools to take part. You can go to we have a web page. You can go to the webpage globalmeteornetwork.org/outreach, and that will give you more details about the program. Also on that website, there's some tutorial materials that you can take a look at. There's a complete tutorial on meteor astronomy. Pretty much everything that I've given you in tonight's talk, you can find it there. There are also tutorials on how to use the desktop planetarium program Stellarium, and there's some nice little extramural exercises and things as well there. So that's all on the GMN outreach program, and both myself and Pierre are we're on the global team for the outreach program. You can also then, if you want to email me, my CAM address, this is Comet, Asteroid and Meteor at ASSA, or you can email Pierre de Villiers at the outreach address at ASSA if you want more information on how you can participate. We have a WhatsApp group. It's the Global Meteor Network ZA, which is administered by Andre Bruton. So if you want to get involved and you want to get onto that WhatsApp group and discuss things together with experts, we can do that for you. And And then finally, I encourage you to download the Meteor Journal, eMeteor News. It's a fantastic journal which is issued 6 times a year, so every 2 months. It carries articles on meteors. All the results on new shower discoveries are listed there. And if the South African cameras have participated in that discovery, you'll see mention of it. It's completely free of charge. It's a fantastic journal. All you've got to do is go to emeteornews.net and you can download for free the Meteor Journal on a regular basis. Okay, so in conclusion, we've seen that South Africa has played an important role in the early imaging of meteors. We saw that with Lewis Elkin and also the work that was done at Boyden in the Free State. In the same vein, we want to continue to play our part in understanding the meteor showers of the Southern Hemisphere. Our cameras have already participated in the discovery of several new meteor showers, and many more remain to be discovered. We desperately need to improve the detection of fireballs that could lead to discovery of meteorites on the ground. And with that, I thank you.
Thanks. Very fascinating. Involved in you finding. I think there's probably quite a lot you didn't mention in a short talk like this. You made a catalogue of South African fireballs detected going back quite a long way. Can you elaborate a little bit on that?
Yes. So the Southern African fireball catalogue, it's a complete record of every fireball which has appeared or been reported to ASSA since I took over the section in 1992. These fireballs used to be reported to our monthly notes, and I decided when I took over as director to actually catalogue, investigate and catalogue every fireball which has been seen. I think we're up to 546 was the latest. It was a fireball seen yesterday. And so that catalogue of 546 fireballs, all investigated, is complete. It's going to be put online on the ASSA webpage so anybody can go and have a look at it.
Fantastic. Many thanks, Tim. If the audience would like to ask questions, just ask me and I'll just repeat them so that they can be recorded. Go ahead.
You could tell us why the USA there was very little representation of cameras in the global map of the USA. Why would that be?
So the question is, why is there very little representation from the USA? On your map, I think of red flashes, there were quite a few pinpoints I saw, but they looked very faint. Or is the map just not big enough, detailed enough? So the USA, why are they not more involved? Is the question.
I actually can't answer that. I don't know the reason why there is quite a lot of representation in the USA. I mean, on the West Coast in California, there are a lot. There's a very high concentration of cameras on the East Coast, but on the Northeast side. So, you know, the server for the GMN is in Canada. And so there's a big concentration of cameras in Canada. But for whatever reason, Europe really has pioneered the GMN. The UK particularly, also in the Benelux countries, Belgium, Netherlands, and Luxembourg, they started off with cameras, and now pretty much all of the guys and Benelux has been very active meteor observers for many years because of the cost of these GMN cameras are so cheap. Comparatively, all of the Benelux guys have converted to GMN. So there's a very high concentration in Europe. I think the Americans will follow suit now. The GMN is really starting to get going, and so you'll see more and more GMN cameras sprouting up in the US.
Okay, are there any more? Other question, David?
showers, are astronomers using them to try and find the source of those meteorites? In other words, I think the figures were many, we don't know the source of them.
Yeah, so the question is, I don't know if you can hear it at all, Tim, but the question is all these meteorites which are detected, but the sources are not found. David wants to know, are astronomers trying to find these sources? It
Yes.
seems like a very large fraction is unknown.
Yes, that is the goal is not only to find meteorites, but actually to backtrack the orbit so that we can find out what the parent body was. That's exactly what happened with the meteorite which came across Botswana in 2018. The asteroid was 2018 LA, and we managed to actually track that back to the asteroid Vesta. Not only were we able to track it back to the asteroid Vesta, but we were actually able to determine exactly where on Vesta it came from. So if we can triangulate these fireballs very accurately, we can backtrack, we can determine an orbit, and we can determine exactly where it came from in the asteroid belt.
In that case, you actually found the meteorite on the ground, did you?
We found 22 fragments on the ground. I found one of the 22 fragments. But yeah, we managed to determine the fall location very precisely. And then actually several teams over a period of months went out. And in total, we found 24 fragments of that, which are now called the Motopi Pan meteorite.
Interesting. So yeah, we're all interested in a bit of astronomy, but those are things that are, very many light years away from us. We can only see it through telescopes, but these things fall on our heads, so that makes them very interesting.
Yeah.
Another question? Okay.
Yeah, from Chris.
Sorry, just a second. Chris, we just got another question going, but you can just go ahead with your question then, Chris.
Okay, sorry, I actually have three, so I will wait my turn. I just didn't find a place where I could raise my hand.
There is one somewhere. I'm not quite sure where it is in the video.
Yeah. Okay. Firstly, in the early part of the presentation, you showed the path of the Geminids' origin, the phaeton.
Yes.
And I noticed that the trail is very dispersed at aphelion and condensed at perihelion. Is this because of radiation pressure from the sun, or what?
Yes. Yeah. So it's a combination of factors, Chris. So that's just a computer simulation. What they normally do is they take 1 million particles with different sizes. They put in planetary perturbations to take into account the effect of mainly the planets Jupiter and Saturn on the particles of different mass, and then also the effect of solar radiation pressure and the effect of the solar wind. And they gradually disperse the particles further out into the solar system.
The second question is, do the parent bodies tend to cluster near the plane of the ecliptic? I mean, we see meteors coming from everywhere, but I would expect there would be some preferential condensation.
Yes. So if you look at all of the showers, we get what we call the ecliptic showers. And so there are a lot of showers in the plane of the ecliptic. And most of those are divided up into northern and southern branches. There are a lot of showers which we call also Helian meteors, which appear to come from the direction of the sun in the plane of the ecliptic, and then the anthelian meteors, which are meteors which approach from the opposite direction of the sun. And these are all residues of comets and asteroids which are located within 15 degrees of the ecliptic.
Thanks. The third question is on a practical note with the cameras. Do you have problems with birds fouling the cameras?
Not that we've noticed. I think there may be the occasional problem with spiders and spiders' webs and things like that. But we haven't noticed for most cameras around the world that that birds sitting on them and affect them in any way.
South Africa, you might get baboons hanging, especially in Amanus.
I missed that.
In South Africa, you might get baboons hanging on them.
Ah, yeah. Okay, so you need to put the camera somewhere where that's not going to happen.
Right. Thanks, Tim. Nice talk.
Thank you.
Thanks, Chris. Elaine, your question?
I assume you can analyze the composition of the fragments.
Yeah, Elaine was just asking about the analysis of the composition of the fragments. You said it came from Vesta, did you? That was the one in Botswana, 2018.
Yes. So that was analyzed as a consortium. There were 56 researchers busy on that particular. So its composition has been analyzed in great detail. We now know that it's what we call an HED, howardite eucrite diargenite. I'm not a geologist, so don't ask me for the exact composition of it. But if you go onto the internet and you just type in HED meteorite, you'll find exactly what the composition would be. But yes, that particular meteorite was analyzed with literally every technique that we could find.
I think I remember seeing in your catalogue of the South African recorded lowlands that 4 of them hit the ground in Southern Africa at various stages. Is that correct? I think there was one in Southwest, the one in Botswana, the one in Eastern Cape recently, and one somewhere else.
There were 4 fireballs that resulted in meteorite finds on the ground.
Yes.
So it was Monzi, which I think was in Zambia or Zimbabwe. There was Tuati, which was in Lesotho. That was about 20 years ago. Then there was Matopi Pan, which was Botswana. And then very recently, in 2024, was it? August 2024, there was Nkweba in the Eastern Cape. So those are all 4. They were 4 fireballs that resulted in meteorite finds.
Just as a matter of interest, is there any sort of record of all or most meteorites that were actually found in South Africa whenever? Is there something like that, a record of it?
Oh yes, yeah. Everything is summarized on the Meteoritical Society database. So I think there are 51 or 52 finds in South Africa. That's the total number of meteorites that have ever been found here. Whether they're meteorite falls, whether they're from witnessed meteorite falls or found on the ground sometime afterwards. But all of those falls are catalogued.
Audience, any more questions? I think we had a record audience this evening for your talk, which is fitting for the final talk of our year. Thanks very much, Tim. It was really fascinating. Great.
My pleasure, and thanks to everybody for attending.
Online as in the room here. Okay, thanks very much. We'll upload the recording to YouTube and we'll send a link to people that want it. And of course, I'll send it on to you. Thanks, Tim.
Thanks, my pleasure.
Anybody else final comment? All right. Normally, if you were here, we would give you a bottle of wine, but you'll have to drink your own glass of wine tonight.
I'll do so. Thank you very much. Appreciate the sentiment.
Thanks, Tim. See you next time.
Thanks. Take care, everybody.
I'm going to log off now. Thanks, everybody. Any more questions from the online audience? Last chance. All right. No, I see there are a few comments in the chat. I'll put those up as well. Okay. Thanks, Tim. Good night.
Thanks. Good night, everybody.
Bye.